now.
I have to say, got it.
Yes. Very good then. So welcome everyone. It's a great pleasure to have Doug Lynn visiting us to give the Origins Colloquium this week. So as Doug was just reminding us, so I have his biography here. It's a long and distinguished one. He received his actually BS from McGill University in Montreal, and then was one of the first cohort at the IOA in Cambridge. He received his PhD there in, I think, 1976. And was then working as a postdoc both at Cambridge and at Harvard. He joined the faculty at University of California, Santa Cruz in 1979 and has been there ever since, now as a full professor, of course. And along the way has received many awards, Guggenheim Fellow, Otto Schmidt Medal, and Humboldt Fellow, amongst others. He was the founding director of the Kavli Institute of Astronomy and Astrophysics in Peking University in Beijing in, I think, 2007. And so has multiple positions around the world where he's leading a whole host of different research projects ranging from planet formation to star cluster dynamics to the growth of black holes, which we'll hear about today. So welcome, Doug, and we look forward to your talk.
Thank you, Jonathan. It's my pleasure and to join this discussion. And this work is based on the shoulder of many, and many of them are all of them, nearly all of them are students and postdocs, and so it's a very rich field. And part of the reason it's a very rich field is foundation that laid down by the previous workers, including Jonathan. And so I'm going to, let's see if I can get this working. And how do I get to it? Oh, there it is. So I would just be, outline some key points because Jonathan told me this is about 30 minutes and just hit the key points. I won't go through many introductions, and but I will get right down to the point. There are some major issues concerning the origins. For example, when we talk about AGNs, you're usually thinking about the brightest beacon in the universe, and the question comes on what powers it. And the standard assumption, it is powered by accretion disk, and the accretion disk is got its heat by through viscous dissipation of differentially rotating disk. There are good evidence now to suggest that this disk is actually embeds in the disk. There are lots of stars, thousands of stars, and the stars may have provided, at least in some range of the luminosity. So can stellar luminosity power AGN disks? How do stars evolve in the AGN disk if they are indeed powered by stars? And what are the observational constraints and clues? And what are the broader implications on the gravitational wave events and tidal disruption events, and etc. And there are also, as you can see, an incredible parallel between AGN disks and protostellar disks, between star formation around AGNs and planet formation around stars. And then the question is, we have the nearest example of supermassive black hole, namely in Sagittarius A star and near the Galactic Center. And there are lots of clues. And the key question is, what can we extract from this case study about the history and the important dynamical evolution around the Galactic Center? Jonathan, can you remind me when, with 5 minutes to go? Sure. And then, of course, for the general public, there is a question about, can billiard planets form near supermassive black hole? Do we have any evidence of it? One of the major observational motivation to look at AGN evolution of the supermassive black hole is from these luminosity function, evolution of luminosity function of AGNs, and that's obtained from Sloan Digital Survey, and it gives you something about both the mass accretion rate and the efficiency of conversion from rest mass energy into radiation, as well as the close link between that and the Eddington luminosity. Basically, after all of that analysis, you can come down to relatively simple numbers, namely that the mass accretion rate of a supermassive black hole is generally proportional to its mass, and with a efficiency factor that you can link all these things. If you have this kind of feeding of the black hole through an accretion disk at a steady state rate, and then you would be able to describe the key parameters of the structure of the accretion disk in terms of alpha, and which is a viscosity parameter, h is aspect ratio, q is gravitational stability parameter, and then you can work out all of these in terms of the black hole mass and the distance. And very little needs to be extracted from this information, other than the fact that in the outer region of the disk, it's prone to gravitational instability, and in these disks, numerical simulation and indicates that they can indeed fragment to form stars. In addition to the spontaneous formation of stars and around supermassive black hole, there always seems to be associated with a stellar cusp. And so there are lots of these high resolution imaging of HST imagings, and to try to resolve the surface brightness and to indicate that there are nuclear clusters. And these nuclear clusters, if it goes through the disk, they can also be trapped. And so you can have stars form in the disk, and nuclear cluster comes into this region. Now, and like star formation in the GMC, that these stars, once formed, they remain in their nursery, and in this very dense environment that in this nursery, they will start to accrete gas from the disk around the supermassive black hole, and these accretion rates are very, very high. So it powers the disk around the supermassive black hole. You can go through various sources, and the standard source that all of the standard accretion disk is based on is from these viscous dissipation. And then you can add in the stellar luminosity, and then maybe the supernova, maybe the accretion onto the remnants. And then, of course, there's a irradiation from the central region into this different parts of the disk. Associated with this, you can put the stellar heating in terms of the surface density of the star and the individual luminosity. And if these stars evolve off the main sequence, and then you can have a star formation rate to replenish all of this. And this is to be balanced against the cooling from the surface of the disk. And one can work out from there some basic theory on how you can maintain such a disk. And the disk is powered, these stars accrete, as I mentioned, and it's somewhere between the Bondi rate and the Hughes limited rate. You can determine this, and there's two determining factor. One is gap formation. The other is the possibility of reaching near the Eddington limit. When you need to reach the Eddington limit, the radiation pressure and start to counteract against gravity. But in addition to accretion, the stars, when it becomes very massive, is also very powerful sources of wind. especially if it's near the Eddington limit. And so the star may undergo metabolism, and it accretes and it also sheds. And this was worked out together with Matteo Cantillo, and we try to look at the stellar evolution and structure, and if the accreted material is able to mix with a nuclear burning furnace, and then you continually resupply fresh fuel, and then you can actually maintain a forever state. These are forever stars. These immortal stars can reach the mass of close to 1,000 solar mass. And that at that point, the Eddington limits start to play a major role. And then you can keep these massive stars to live forever. And however, if it's in the outer region, they can still evolve off the main sequence. And this is important because during the if it's only during the main sequence, and you can have the conversion of hydrogen into helium through a CNO cycle. But in order to generate anything that is out of the alpha elements and heavy elements, you have to go through post-main sequence. So what can we say from the observations? So recently that I've done an analysis with an undergraduate student, Jiamu Huang, and try to look at all of the available data. And you can see that by looking at the alpha elements at different redshift, and you can get supersolar metallicity from various surveys. And furthermore, it is independent of the redshift. This is completely contrary to what you would expect from the galactic chemical evolution. We all know that when the galaxy was young, it was metal poor, and then it got enriched. How is that possible? So one possibility is that you enrich, and then the gas keep on flowing towards the supermassive black hole. So in fact, you never pollute beyond certain range. So one need to do this in terms of diffusion calculations and see how you can generate pollution and then go down to the black hole. Another important effect is to look at the different elements. You look at whether there are any helium enrichment. This would be the prediction from the forever stars. You only convert hydrogen into helium, so you push it out to the surrounding region, and then the disk becomes more and more helium rich. And then you, if they can evolve off the main sequence, and then they can produce these alpha elements, and or if they undergo explosion, they can produce iron. So we can look at what is called the broadline region, which is in the small region near small radii near the disk, and we can compare it with the narrow line region. First of all, you can see there's a systematic shift in the metallicity. So that means it came in, the gas came in with modest metallicity, but when it eventually got close to the central black hole, the metallicity has got to be very much enhanced to be supersolar, 3 to 10 times solar in the alpha elements. And this is independent of redshift. Let me just say that, independent of redshift. And so this is highly productive in alpha elements. And that tells you that star formation may be very prolific. And furthermore, the iron content tells you it's type 2 supernova, not type 1 supernova that is doing the job. So that indicates the presence of massive star. And the elevation of nitrogen is also important because nitrogen is a secondary element. So it means that there are multiple generations of star. If you just produce from supernova, you produce very little nitrogen. And then through the CNO, nitrogen gets enhanced. So how can you evolve off the main sequence? You already seen it from the Cantillo's result that it gets into this forever state, but that is based on the assumption that there are thorough mixings in the internal envelope of these massive stars. There are radiative regions which can provide a buffer state, so the material comes in, does not mix with the nuclear burning furnace. So the the helium content in the furnace start to grow, more and more modifies the luminosity mass function, mass luminosity relation, and then it actually sheds off a lot of mass because many of these stars will become super Eddington, and so they shed, and then they evolve off the main sequence, and from these stellar evolution we can calculate their byproducts from both main sequence and post-main sequence evolution. And currently, I'm working with Chris Pryor and try to look at the production of heavy elements in through type 2 supernova. And all of these are measurable from the quasar, from the AGN broadline region, and you can make comparisons between iron and magnesium, which is more of a alpha element. And so then you can see all of these are subsolar, as it is similar to population 2 stars in the galaxy. So now I'm moving very quickly on to the next subject, namely the byproduct of these massive stars. If they produce supernova, they produce little black holes. You can calculate the rate from what you measure in terms of metallicity, how many they are produced. So and then figure out whether there's a rich population. Indeed, there could be the presence of tens of thousands of stellar mass black hole within 1 parsec, and these little objects will accrete, and as they accrete, they would also radiate energy to provide energy supply to heat the disk. But what is also very interesting is usually their bounding radius is small compared to the thickness of the disk, so they would experience all of this turbulent background medium, and then the material that gets onto these little black holes will go, it goes through random type of chaotic type of angular momentum spin. And so the little black holes you tend to get it would accrete back and forth with material carrying different angular momentum. So as a result, through this kind of random walk, and then and Yishan Chen has shown that this the spin angular momentum parameter can actually become relatively small. This is important from LIGO sources, because LIGO sources can measure what is called lambda effective, and which can measure the effective spin rate, and they tend to be low in spin rate. And so this is maybe one way to do it. The coexistence of thousands of these little objects also means that they can interact and they perturb each other just like planetesimals. And in this environment, one can calculate what is a merger rate and what these are idealized simulations, and done by Sentai Lee at Los Alamos. And so then the upshot of this is that they capture into binaries and small clusters. In these binary and small clusters, they become more and more compact, hardens, and eventually they get sufficiently hardened. They get down to a few about a solar radii, and then they undergo further orbital decay through gravitational radiation, and one can calculate the rate of semi-major axis reduction and eccentricity reduction, and try to work out what this will do for gravitational wave sources. And that rate is actually very similar to what you would expect out of LIGO. So this is now a small industry of people trying to, do population synthesis for LIGO, and I was born in the late 40s and early 50s, and I remember John F. Kennedy says, and he said that ask not what AGN can do for LIGO, but ask what LIGO can do for AGNs. So I followed that advice and try to figure out what you can do. So now I'm going to turn my attention to the Galactic Center very quickly. And the one supermassive black hole that is being detected had already got 2 two Nobel Prizes so far, and one is from the Popper motion surveys of these S stars, and you see these young stars, and they're only a few million years old, and they the inner region, you have the stars are orbiting in quite eccentric orbits, relatively isotropic, and then you have these disk stars, and then you have off the disk stars. So it's very complex dynamical system. And we know that the black hole's shadow has been detected, and from the Event Horizon Telescope project. And then there's also this detection of what is not a star, but it's more extended resolved cloud. And these are called G clouds as they move around, orbit around Sagittarius A star, and they get stretched out, and then they get compressed back. And another very interesting clue is around Sagittarius A, and then you follow with Chandra, and every day it seems that there are these X-ray flares, and the amount of flare correspond, the amount of energy that's radiated from these flares correspond to about the rest mass energy of a kilometer-sized object. And then they last for about 30 minutes. So the question is, what do these clues tell us? And so if we look at the bigger environment, we see that there are these young stars, and Sagittarius A is sitting right in here, and right in the very central region, those are the S stars, and right down to the bottom. And then in the surrounding region, there are still some young stars, and there's a very interesting cluster, or S13E, and it has maybe a mass of 10 to the 4 solar masses. So compared to the central object, 4 times 10 to the 6 solar masses, the mass ratio is 400 to 1, very similar to Jupiter versus the sun. So now, and then, but there is no disk around there now, and there are these young stars. So how do you, where did they go? And we see around the Galactic Center, there's also the so-called Fermi bubble, and which is detected with Chandra, and so the actually detected with Fermi, and then these bubble, if you trace back, and it tells you that it originated from near the Galactic Center around a few million years ago, and the mass that's contained in this bubble is similar to what you see in the stars. I realize I'm getting close to the end, and so bear with me for another 5 minutes. So in this environment, if the disk comes and goes on a few million year timescale, it's very much like solar nebula environment. And you have these protostellar disk that goes away. And if you have the presence of Jupiter with a somewhat eccentric orbit, and then its secular resonance can propagate through. And it can excite eccentricity like the asteroid belt. And so one can see whether that could play a role in the excitation of these eccentricity for the central S star. In addition, there is also the so-called effect of Kozai-Lidov. In fact, and there's several people have discovered this in advance, von Seipel, Lidov, and Kozai, and so on and so forth. If their orbits are not on the same plane, then there's a torque, secular torque that exerts between them, so the eccentricity and inclination can change rapidly. And we put all of these effects into account in a set of simulation that's led by Xiaochen Chen, Xiaochen Zhang, and she has done the simulation that's in the color dots, and we compared the observation with that from the gravity collaboration, and we plot for the S stars 1 minus E. So this is circular orbit, this is a nearly parabolic orbit versus the peri-astron distance, and the black dots are the observations, and the color dots are the simulation, and these lines, 100%, 20%, 5%, 1% is detection probability. The fact you don't see anything here means that there is they just cannot be detected up to now. Okay, but down here you can detect 100% of the time. There's nothing you see around here. And so the IMC in our model is somewhere up here, the intermediate mass companion. So the idea is that the simulation is based on this kind of cartoon picture that during the depletion of the disk and after the star was formed, and then this combined effect of the Kozai effect and the secular resonance actually excited the eccentricity, and then you have some intruders that went into the inner region of this major disk, and so it's further away from the IMC. But by bringing in highly eccentric orbits, and you can actually excite resonant relaxation, and then you can produce all of these type of process. And we carefully analyze and the evolution path, and starting from nearly circular orbit, and then eventually, because of these secular perturbation, how within a few million years, the lifespan of these S stars and disk stars, you can produce that. You can also see by looking at the three-dimensional images and whether they're the presence of some additional components. And this is how observers and the gravity collaboration, they work out these. This is a distribution of the angular momentum vector in the frame that's centered around the galactic center, and then try to see things like this is S star, and there's this star, and then they claim that there is a possibility of a second disk, and so the questions, can we reproduce that? And it turns out, because of the secular perturbation and relaxation, we can indeed produce the presence of what looks like a bimodal, slightly bimodal distribution of not only the stars in this region, but also there are these additional contributions. So, with high metallicity,
Doug, you can have 5 more minutes, and that will be fine, Doug.
Okay, I will finish definitely very quickly. Okay, so you have high metallicity, and then all those people who work on planet formation realize this is a great way of producing planetesimals, because when the heavy element becomes large, you have sedimentation of the dust, provided they can condense. If they can condense out at nearly 1 parsec region, there's these dusty tori around AGNs, and that they can condense out, and then they can grow, and their self-gravity can overcome the sharing instability, and then they become unstable. And so this way you can produce lots of little planetesimals, and these planetesimals get scattered through the secular perturbation by this IRC 13E, and then it gets to the vicinity of the supermassive black hole. In a way, it's very analogous to Oumuamua and interstellar object that would, or comets, and they can come very close. They feel the tidal destruction, but because they have these material strengths, and they can break up into small clumps, as you can see in Shoemaker-Levy 9, and this is our original interpretation of Oumuamua, and you don't need a spacecraft. And under these combined effect of material strengths and of various kind, these are the material strengths of regolith, and this is material strengths of a rubble pile, and you can see as they approach, if their perigee gets close to 10 gravitational radius, all of them will be destroyed. This is much closer in than the standard Roche limit. That limit is based on just using gravity as a cohesive force, and here is using material strengths. But as we know in AGNs, especially in the galactic center, the shadow of the black hole tells you there are some gaps there. So you can calculate the friction exerted on these objects if they can come in. And with that kind of friction, you can produce things like meteorites, and then under some circumstance, meteorite can even explode. And this is our model for these flare in Sagittarius A. So, of course, around the more massive black holes, and then you can actually have even lower material strengths. You can get all the way down and to the proximity of the event horizon and raising the prospect of visiting these supermassive black holes, such as that around M87. And maybe there's some people in the audience would be the volunteers. And so here are the take-home messages. And if there's too much to read in here, but one thing that I want you to keep in mind is that AGN disk is remarkably similar to protostellar disk in every way, both in terms of the structure and in terms of possibility of containing sub byproducts, and then in terms of dynamical evolution. And it's just a scale-up version of a protoplanetary disk. So with that note, and I want to say thank you.
Great, thank you very much. So now we have time for questions and discussion, and there's lots of material here that you've covered here, Doug. That's great, and lots of big open questions. So we'll take, if people have burning, well, if people have questions, please raise your hand, and people in the green room.
I'm going to bring down the PPT so I can see people.
Oh yeah, that's fine.
Yeah.
I see Il-Sang first. Yeah, please go ahead, Il-Sang.
Hello. I'm sorry if I'm allowed to ask this question as a remote participant. If there's any, the burning question.
Just go ahead, Il-Sang.
Yeah. Thank you, Doc. It's a very nice introduction. I'm very curious, as you said, I'm interested in and asking a question like, okay, what LSSD does for the AGN? Like you said, like what LIGO does for the AGN. I mean, the LSSD is going to operate it soon, and 10 years of the cadence that we have, the range of the observation from the many supermassive black hole from all the AGN and exogalactic system has a time variability. So if this picture you just introduced could be constrained if we have the LSD data in terms of the populations of mass spectrums and the dynamical evolution timescale, is there anything we can learn from using the LSST to understand better this picture that you just introduced? Do you have any comments?
That's a very good question, and haven't thought through this very carefully yet. I'm just going to make some off-the-cuff remark. The stellar evolution, if they occur, and there will be transit events, such as things like supernova, and but they're in the background of a very bright disk. So the question is, can these events pop out from the background of this disk and then give you signatures? And
well, if black holes swallow those, the thing, that's the AGN varies. Is it still possible?
Well, most of the parts are, even though that we're talking about within 1 parsec. 1 parsec for a supermassive black hole is still 10 to the 5 gravitational radius.
Right.
So, and most of the star formation occurs beyond a few hundred gravitational radius. But some of them may migrate. Okay, so, and if they do migrate into the proximity of the black hole, and they could produce observable signatures, and including in some cases, as we calculate these questions concerning the supernova, and a question is whether they can actually produce gamma ray bursts, and whether they can produce events that we can clearly identify. But as you can see, maybe even some dormant black holes, not AGN, but DGN. So I would ask you to concentrate on DGN when the disk goes away, and our galactic center is a DGN. Okay, and when the disk is not there anymore, but there are still stars that form that outlast the disk, and if they undergo these TDE and if they undergo this type of process, it would be very interesting because to associate TDE with some events of recent, what looks like a recently extinct AGN. And but we want to explore further on the observational side. I'm just making off the cuff remark, and but we need to do more on this population synthesis.
Right. Thank you very much.
So Joe or Ryan, if you can help me moderate what questions in the room there, but otherwise on Zoom, please people raise your hands. I don't see anything yet, but perhaps
Jonathan, we have one question in Virginia.
Oh yeah, please go.
Yeah, so I have, oh, yeah. Okay. So I kind of have a detailed question for the lead-off COSI page, if you can go to there.
Okay, yes.
So you were talking about you were bringing eccentric orbits to break the resonance. Could you elaborate on that a little bit? What resonance, just the lead-off COSI resonance, or?
Okay, so in the absence of any companion, okay, and the stars in AGN will undergo relaxation. Okay, so now we all know about relaxation in the context of globular cluster. And these relaxation in globular cluster, they're very random. Okay, and I'm still searching for the right reference, right frame. Okay, so bear with me, even though the background is flipping back and forth. What Rauch and Tremaine did was that they say, this is, when you look at AGN, it's like solar system analog because the gravity is dominated by a central source. So all of the orbits are more or less Keplerian, and they're eccentric, and they have a pericenter direction, and they have a semi-major axis. And what is important in celestial mechanics is what is called secular perturbation. Secular means long-term. Which the perturbation of neighbors accumulates from time after time. And these accumulation, oh, I know where it is. These accumulation leads to eccentricity excitation between two bodies. You exchange angular momentum, the two bodies, the body that loses angular momentum, the eccentricity gets excited. And the body that gains angular momentum, that the eccentricity gets diminished. And then likewise in COSI leadoff, and you're exchanging angular momentum. You don't change energy. Okay, the characteristic of these type of interaction is the semi-major axis is preserved, but the eccentricity inclination change back and forth. So now, in order for that to happen, you have to be able to give and take. If you're on a circular orbit, if two objects are already on a circular orbit, they both have the maximum amount of angular momentum for their given energy. So they cannot excite each other unless they can change their semi-major axis through the standard two-body relaxation. That takes a long time. Okay. So now, if you can introduce from your companion, this IMC, and that introduce the excitation from the outer region of very eccentric orbits, and they can venture into the central region, then you're bringing in material, these bodies, which have very low angular momentum. And then they can exchange angular momentum, the eccentricity with object near the center, and then you can actually relax relatively quickly. Rauch and Tremaine refer to this as resonant relaxation. In celestial mechanics, people like in celestial mechanics, we refer to this criteria as a Jack-Lescar as angular momentum deficit. So you need to have a removal of some angular momentum for the eccentricity to get excited, and that is called the angular momentum deficit. Deficit meaning the total amount among all the stars in this region that you actually do not have the maximum amount of angular momentum to give you the circular orbits. So, and that relaxation can be short. But if they start on circular orbit, they can't do it. So the only way to do it is to bring in stars into the inner region that has low angular momentum, and then they can undergo resonant relaxation. So this is the result when we analyze the simulation. We see this very clearly.
So Doug, if I may, can I paraphrase what you're saying then? So the eccentricity of the S stars, if they formed in a disk, requires that some intermediate mass object, you're proposing this IRS-13 cluster, had certain properties that allowed these stars to come in, or it could be an intermediate mass black hole, I suppose.
Yeah, it could be. It could be. I try to avoid being overclaimed. Yeah, yes, absolutely.
But you would need this IRS-13 to have existed for a certain amount of time and not be tidally disrupted itself, and that's all consistent with its properties, its known properties.
Yes. Okay. So there are two things. One is that relaxation can always bring in eccentricity, but the problem is that these stars are very young. They're only about a few million years old. They already gained their bad habits. So how can you gain the bad habits so quickly? Okay, if you just rely on the young stars themselves, they can't do it on this time scale. So you've got to have a perturbation, and the perturbation is not close encounter, it's distant encounter, just like the influence of Jupiter on us is not because we have gone near Jupiter, but Jupiter's effect can still influence our orbit. Okay, so this is so the secular perturbation is average over orbit. So that means that this IMC, the intermediate mass companion, need not be a coherent entity. It could be a coherent entity, and we try to identify it with IRS-13E, which could have preserved its entity. But even if it's broken up, being broken up, remnants of a dense stellar cluster, and then the orbit of all of the debris still follows, just like a cometary tail, a cometary stream. It still follows the same orbit. So, and that all of the subcomponents, the broken up components, can actually contribute additively to the excitation of distant objects, the eccentricity of very distant objects. And what is interesting is that people are starting to measure pulsar motion here, and they see the pulsar motion of this IRS-13E is very similar to the so-called second disk, pseudo disk of stars. So, and that gives us some confidence. And in addition, we think that you can measure whether it's a genuine entity and whether it's a bona fide object like a IMBH. And then its perturbation, its impact on the orbit of S stars, you can actually measure with the pulsar motion of the S stars, and they will undergo precession, primarily dominated by a post-Newtonian correction. But the fact that there are these secular perturbers out there, and they would be a departure from a post-Newtonian. So as the gravity experiment continues and into the next decades, and very precise measurement of pulsar motion can actually tell us where are the culprits.
And just concluding this point, I mean, I'm interested in general to constrain populations of intermediate mass black holes that might be present. If you had too many intermediate mass black holes or population of them, can you comment about, right now you need one object, but
Yes.
if you had, I don't know, 10,
Yes.
all working in different directions, would you have any constraint on that?
Yes, there's already very, very strong constraints on intermediate mass black hole around Sagittarius A in the very central region. Fortunately, the region that I'm asking, because I don't need them to perturb with close encounter, so I'm putting it out to at 0.3 parsec away, okay, which is the projected distance between these objects, and even at just like Jupiter can influence us, and Jupiter is at 5 AU, we're at 1, and so you can make it fairly far away. So the constraint that is produced, that people have made on the Galactic Center on intermediate mass black hole, is outside, it's in this region, and we're way out here. And that constraint is not very strong. But eventually, when you measure, if you can measure the precession of the S stars out to some region, and then these will really give you a very strong indication what the mass is, and there are observable constraints.
Great. I have many more questions, but if there are others now from the room or in Zoom.
Jonathan, could I ask a question?
Sure.
Yeah, I had a question about these forever stars, about the geometry. So are they accreting material through a disk-like structure and then ejecting it through a jet, or is it both spherical, the accretion and the ejection?
So this is a detail that is currently being investigated by Yixian Chen, and by looking this exchange, with Yanfei Jiang, and you have radiation pressure trying to push things out, and you have gas comes in. So either you have a disk or you have something like that. And the reason I said either is because in the standard planetary accretion, we think there is a planet, and then it's fed in from the protoplanetary disk, and so it forms a disk around this region. And but in this environment, because it's very turbulent, and this disk may actually change orientation very quickly, and on the time scale of the orbital time scale of the big guys. So if you change that, let me see if I have it here. And oh yeah, and then the accretion, it's very hard to form a disk on short time scale, because the FID or the gas supply actually goes through some sort of random walk. It's a very stochastic type of process. So there may not necessarily be a disk. And those are calculations that we are trying to do lots of simulations on. But really, whether they are forever, they become forever star or not, and does not depend on this larger environment. It depends more. Let me see if I can. Somehow I'm unable to move my. Okay. Let me see if I can. It depends more on what's on the inside of the star, and it's a separation between the nuclear burning zone and the material that actually got onto the disk. So the question is more to do with whether there is a radiative layer here. Okay, all massive stars, the radiative layer becomes thinner and thinner, but it's still the question is whether this radiative layer can actually help you to mix the material that you just consumed with the material the ashes that's already burned. Okay, if this material that is just consumed can get down to the nuclear burning furnace, you have metabolism, and you have, fresh supply, and that's how you can keep it forever. Now, so the massive star community wants to have this mixing because they want to explain many observational evidence in these isolated massive stars. But if the stars are not rotating very fast, because all this random type of accretion event, and you may be able to maintain in the inside this radiative layer. And if there's no mixing between these radiative layer, when we do the Maser calculation again, indeed, the helium content in here elevates and gradually accumulates, just like what you would do with an isolated massive star that's not rotating. And then they will evolve off the main sequence. Then the helium burning will start to take place. Then you, through triple alpha, you generate the alpha elements and so on and so forth. That's what the difference is. Why you should have forever star versus a evolved star.
So maybe, Doug, I would like to bring this back. I think there are two main things here. And your main point about the AGN disks and the similarities to protostellar disks. So the first question is, to what extent really are AGN disks prone to fragmentation and star formation? You know, in the past, also with the work we did with Jeremy Goodman, and Jeremy has thought about this for a long time as well. He was concerned that most of the mass flux would get diverted into stars rather than be able to even make it to the AGN, which is very different from the protostellar case. So the direct evidence we have for these disks fragmenting into stars, there's the Galactic Center that we've discussed. You mentioned the metallicity, although I wonder if, how robust that is, if it could just come from metal-enriched gas from a wider region. So it's my impression that there's relatively limited direct evidence for star formation in these disks, except the Galactic Center case. And then if star formation does happen, then what mass the stars achieve, and is the IMF different? And again, the Galactic Center is the one good case where we have evidence for that the IMF is different. But can we predict what the mass should be of these objects? So I don't know if you want to take the first.
Yes, I can put all of those things together. Yeah. Okay. First of all, this picture, this frame, involves Jeremy Goodman. Okay, Jeremy is one of the co-authors of this paper with Yishen. Yishen now is a third-year grad student under Jeremy's.
Yes. Mm-hmm.
Okay, so the cooling and heating and fragmentation, and they take into account. But let me just say that even though many of the stars goes into stars, but if they evolve off the main sequence and they shed, okay, they return back the gas. So because the star formation is this conversion, you basically use this efficiency factor of 0.007 from hydrogen into helium, and you can actually work out and the possibility of continuous percolation, and versus the possibility of many this total consumption. And in fact, this is a paper that I'm writing with Yishen right now, trying to look at this very question, under what condition you get into a starburst scenario, under what condition you get a gradual percolation type of situation. With regard to what is direct observational evidence, and this is exactly the point I want to make. Okay, here is a narrow line region, and we analyzed exactly the same, similar type of AGN from their spectra. And there is a narrow line region and there is a broad line region. Let me remind you that narrow line region comes from further out in the disk, and the broad line region comes from way in. And I think I have a slide to, sometimes this doesn't quite work. Okay, I probably removed that slide already. Anyway, so if you see that there's a systematic difference in all of the elements in the broad line region compared to the narrow line region, then it tells you there has been metallicity enhancement from here to here.
Mm-hmm.
Okay. And so that is one, perhaps, circumstantial evidence. Another circumstantial evidence is that if you had star formation here, and you can calculate the surface brightness of the disk at different locations, Circle and you and others have done it in the early 2000s. Okay, now today we can actually measure all these from microlensing, dissecting of brightness across the AGN disk. Because you see these AGNs are lensed by foreground galaxies, but they are composed of lots of stars. And the individual microlensing can actually probe right into the center. So you can actually look at the brightness profile, and that's departs from what you will call the standard viscous evolution of disk. And you need enhancement. You need auxiliary power, in the words of Jeremy Goodman. Okay, and then you can also look at this. That's a second piece of evidence. The third piece of evidence would be that what you see is in the SEDs, the spectral energy distribution, they don't fit the standard alpha disk model. And then we can also do this with reverberation map. We try to do it with a reverberation map when the central luminosity shines, and then there's a time delay. And we can use that to measure the profile, the aspect ratio, and we can measure things like where the emission lines come from.
Mm-hmm.
Okay, and then we can probe how these processes can take place. And I think finally, the piece of really strong evidence is that metallicity in AGN disk even becomes supersolar at ratio of 7 to 10.
Mm-hmm.
Okay, and while the host galaxy, there's no such a metallicity at that early stage. There's no leftover stars, and yet the central engine seems to be heavily metal rich, but
Right.
the
Yeah,
surrounding
maybe a
region
key, I
isn't.
think. So there are metallicity measurements at the highest redshifts now.
Yeah, some even up to 10. The iron becomes solar in many of the cases.
Right. Well, yes, that would be very interesting. Very good. We can transition into a more general discussion where we can also show things. I may stop the recording in a second now, unless there are any last questions people want in the recording.